Hello everyone and welcome back to Atmospheric Soundings. This is part of Lab 2 and we're pounding our way through the SkewT log P diagram. This video will cover temperature inversions, also will help you identify clouds on the SkewT log P, freezing levels, and also how to identify the tropopause. So we'll start out with temperature inversions. By definition, straight out of the glossary of meteorology, the definition of a temperature inversion is a layer in which temperature increases with height. You probably knew that already. And in the calculus form, it's dt dz is greater than 0. It's an inequality telling you that temperature increases with height. On the sounding, you can see a layer in the lower layers of the atmosphere where temperature is in fact increasing with height. And there are a lot of different types of temperature inversions. Here's a few of them, and these are the ones that you see on soundings quite frequently. Subsidence, frontal, radiation, and also turbulent inversions. We're going to talk about subsidence, frontal, and also radiation inversions. On this sounding that we have here in this diagram, you can actually see two inversions, and perhaps a third layer in the upper atmosphere a little bit higher near 500 millibars where the atmosphere is isothermal. Temperature doesn't change with height. So radiation inversion is caused by the sun setting. As the sun sets, there is no longer solar radiation coming in to offset the loss of radiation from the surface, infrared radiation, which is constantly leaving the surface of the Earth both during the day and night. During the day, the temperatures don't cool off because solar radiation is greater than the outgoing infrared radiation from the Earth. At night, since there's no solar radiation, you have all infrared radiation going out. No compensation. As a result, the Earth loses energy, its temperature cools, and the air in contact with the ground cools. So as a result, you have this layer that's probably anywhere from 100 to maybe 500 feet thick, maybe even more, where the temperature increases with height. At the surface, it's cold. Aloft, the air temperature doesn't change that much. It's away from the surface of the Earth, and you see this strong inversion. We call these radiation inversions. Here's another type of inversion. Fronts, we'll see, are very stable layers of air, and when a weather balloon or radiosonde goes up through a front, you'll see a temperature inversion. Down below, the air will be colder. Up aloft, it'll be warmer, and a line connecting those two results in inversion. One way to identify frontal inversions is to look for change in wind direction and or speed depending upon the altitude. Down low, it'll be more directional changes. Up high, it'll be more speed. We'll talk more about this when we get to cross sections. Another type of inversion is a subsidence inversion, and this occurs when layers of air sink, and as they sink, they warm dry adiabatically. So you'll see a temperature profile in the atmosphere that is very close to dry adiabatic. So those are your temperature inversions, different types. You will not need to identify inversions in this lab, the different types, but you should generally be able to identify the inversion by itself. Now we'll move on to clouds, and on soundings on the SkewT log P diagram, we assume that there are clouds when the temperature and dew point are within 5 degrees Celsius of each other. Since instrumentation isn't 100% reliable, you're not going to get total saturation. Not only that, but perhaps maybe a radiosonde went up in a hole between clouds. The dew point will get closer, but it may not be exactly the same, the temperature and the dew point. So whenever it's very close together, typically 5 degrees Celsius or less, we assume that there are clouds. Here's an example, and this is a very good example where it went right through a cloud, and you can see the temperature and dew point are right next to each other. But sometimes they're close, and sometimes when they're close, we can infer that there are clouds. Another thing that we can identify in the SkewT log P diagram is the freezing level. And by definition, the freezing level is the height in the atmosphere where 0 degrees occurs, 0 degrees Celsius, that is, 32 degrees Fahrenheit. So if you know your altitudes for standard levels, for example, you should know that 925 millibars is 2,400 feet MSL. You should know that 850 is 5,000. You should know that 700 millibars is 10,000. And then finally, 500 millibars is 18,000 feet. And that will help you identify the different layers or different altitudes of the freezing level. So what you can do is you can look at the 0 degree isotherm and where it crosses the temperature profile in the temperature profile as measured by the radiosonde. So in this example, you can see 0 degrees Celsius, follow that isotherm down, and it hits the sounding somewhere between 900 and 800 millibars. It's a little bit above 850, and guessing on that, I can probably guess an altitude of maybe about 5,500 feet or something like that, just as a ballpark figure. Sometimes when the sounding goes up through the atmosphere, there will be multiple freezing levels, and it's kind of important for pilots to know about this because it tells them where they can expect icing and where they may not expect icing. Also, this is important for forecasting different types of precipitation. For example, here's a particular day in the winter. You can see Jackson, Mississippi is receiving rain, and Little Rock, Arkansas freezing rain, and Springfield is receiving snow. The different soundings for each location: Springfield, where it's snow, you can see the temperature is entirely colder than 0. Little Rock, where they had freezing rain, you can see that there's a warm nose, and then the temperature once again gets below 0 near the ground. As precipitation falls, it melts and then refreezes before it hits the ground. Is almost entirely warmer than 0. There's a little nose that's colder, but they didn't experience freezing rain on this day. They did experience rain. Finally, the last thing is the tropopause, and the height of the tropopause is the lowest height where the temperature lapse rate decreases to 2 degrees Celsius per kilometer or less. In other words, you're going to see a significant change in the lapse rate. And looking at this sounding, you can see how the temperature decreases up to about perhaps 150 millibars or thereabouts. In the radiosonde data, they actually give you the tropopause. They calculate this, but you can eyeball it typically by looking at a large change in the sounding profile. That's all I have for you for this video.